Born-Haber cycles. As we know that Born-Haber cycles is an energy cycle that shows the enthalpy changes in the formations of an ionic compound. And we use it to calculate the lattice energy or unknown enthalpy of an ionic compound. We can calculate the lattice energy by using energy cycle diagrams or energy levels diagrams. So in this diagram, we can see that if we need to change the metal or non-metal into the isolated ion, we need to use standard enthalpy of dissociations or sublimations. And if we need to change the isolated atoms into isolated ions, we need to use standard enthalpy of ionizations and electron affinities. Then isolated ions can turn into the ion crystals by standard enthalpy of lattice. So this means that heat changes when one mole of ionic compounds form from its gaseous ion. Then the metal and non-metal can turn into ion crystal by standard enthalpy of formations. In this chapter, we also learn about electron affinity. So the definitions for it is the energy released when one mole of gaseous atoms gains one mole electrons. So and here we can see the oxygen atoms in gaseous phase will gain one mole of electrons and turns into the oxygen ions. The second one is first ionization energy. It is minimum energy required to remove one mole of electrons from one mole of gaseous atoms in its ground state. So and here we have X atoms in gaseous phase, and it can release one electron and turns into X ions in gaseous phase also. And we also learn second ionization energy. Second ionization energy is the energy required to remove one mole from one mole of gaseous ions in its ground state. So and here we have X atom in gaseous stage, so it can turn into the X atom also with the charge 2+ and release one electrons. So to draw the Born-Haber cycle, we need to know the type of enthalpy. We learned 6 types of enthalpy, and the first one is standard enthalpy of formations. So it is heat change when one more compound forms from its elements at standard state. So this is the examples for the enthalpy of formations. It is formations of carbon dioxide. So at here we can see that carbon dioxide formed from the atom of carbons and also oxygen molecules. So we also need to take note that this is one more CO2. The second one is standard enthalpy of combustions. So it is heat released when one more substance is burned completely in excess oxygen at standard state. So this example is about combustions of ethane. So at here, the ethanes burn in excess oxygen and form carbon dioxide and also waters. For the third one is standard enthalpy of Atomization. It is about heat absorbed when one mole of gaseous atoms is formed from elements at standard stage. And the example is atomization of chlorine gas. So at here, the definition is about heat absorbed when one mole of gaseous atom is formed from elements at standard stage. So and here we have 2 more atom chlorine, so we need to multiply 2 for the standard enthalpy. And we also learned the standard enthalpy of neutralization. It is heat released when one mole of water is formed from the neutralizations of acid and base at standard stage. And here we have HCl as an acid and NaOH as a base. So it will form salt and also 1 mole of waters. We also learned the standard enthalpy of hydrations. So it is heat released when 1 mole gaseous ions is hydrated in water to form hydrated ions in aqueous solutions. So and here, these chlorine ions in gaseous stage will form the chlorine ion in aqueous phase. And the last one is standard enthalpy of solutions. It is heat change when one more substance dissolves in water to form a very dilute solutions. And the example is the dissolving of ionic solid in water for NaCl. So here, this NaCl dissolve in waters and it will form ions Na plus and also ions chloride. And this is all the definitions about the types of enthalpy.
Now we will explain about the step to construct the Born-Haber cycle. Basically, Born-Haber cycle is something like the application of Hess law. Step 1 is to list out all the information given by the question. We will have the standard enthalpy of formation, the enthalpy of atomization for cation or anion, and also the ionization energy of the cation and electron affinity of the anion. And maybe we will need to find the lattice energy if given by the question. Also, the question will require us to find the another enthalpy if the lattice energy is given. For example, the lattice energy, first electron affinity, first ionization energy, and enthalpy of ionization is given. The question may require us to find the standard enthalpy of formation of the compound. The step 2 is to construct the Born-Haber cycle. We will have the two types of the Born-Haber cycle. The first one is simple Born-Haber cycle. We also call it energy cycle diagram. And the second one is energy level diagram. And after having this all the information, we will need to label the enthalpy. When I do this question, I will label the enthalpy of formation as the first one, and enthalpy of atomization of cation is the second one, and the anion is the third one. And also, the fourth one is the ionization energy. The fifth is electron affinity. Sometimes the question will give us the Mg2 plus or Cl minus or O2 minus. When the Mg2 plus is given, it may have the first ionization energy and the second ionization energy. If O2 minus is given, it will have the first electron affinity and the second electron affinity. After having all this information, we may construct the Born-Haber cycle to calculate the value of energy. Here I have drawn two of the Born-Haber cycle. The first one is the simple Born-Haber cycle, and this one is energy level diagram. As we stated, the Born-Haber cycle is the application of Hess law. In this simple Born-Haber cycle, first one we will write about the enthalpy of formation, standard enthalpy of formation as the first equation here. And I write the example for solid A plus the gaseous atom of B. It will form the solid AB. And this second one is the enthalpy of atomization of cation. It will form the gaseous atom of A. And this third one is the enthalpy of atomization of anion, will form the gaseous atom of B. This fourth one is the first ionization energy of A, so it will form the A plus. And this one is for the electron affinity, it will form the B minus. At the end, we will form the solid of AB. Here is the enthalpy of lattice energy. That's all for the simple Born-Haber cycle, and now we will move on to the energy level diagram. When we have the energy level diagram, we need to draw this y-axis. Here we will write about the enthalpy, and we will start from the zero. First one, this is the enthalpy of atomization. In this energy level diagram, we will not do like the simple one-Haber cycle. We will do only from A. It will have the gaseous atom of A, and here we will write back the 1/2 gaseous atom at the second floor. Here we have the atomization of the B atom, so we will have the gaseous atom of B. And here is we will write about the first ionization energy of A, and this one is the first electron affinity of B. After have the first electron affinity of B, we will form the AB solid. Here we will have the lattice energy, and actually this is the standard enthalpy of formation. After doing all these steps, we will need to write back the equation. We will have this enthalpy of atomization plus the first ionization energy and first electron affinity, then plus the lattice energy, and then all of this equal to the standard enthalpy of formation. So that's all for the part of step of the Born-Haber cycle.
The question is, thermochemical data for the formation of sodium oxide is given in table 2. So this is the information given by the question. Ionization energy of sodium is positive 496. Enthalpy of formation of sodium oxide is negative 414. First electron affinity of oxygen is negative 141. Second electron affinity of oxygen is positive 750. Enthalpy of atomization of oxygen is positive 249. Static energy of sodium oxide is negative 2478. So first we have to construct a Born-Haber cycle for sodium oxide. We write out the equation first. 2 sodium plus half oxygens will form Na2O. So we look at the sodium first. We have to change the sodium from solid state to gaseous state. So this is the information that we cannot get from the table. So we just write a symbol, and then we have to change the gaseous form to ion. So the energy is the enthalpy of atomization is ionization energy of sodium. So the value is 2 times 496. Then we look at the oxygens. We have to change the oxygen from gaseous molecule to atom. So we use the enthalpy of atomization of oxygen, and then the value is 249 kilojoule. Then after we get the oxygens in gaseous form, we want to change it to ion. So the value is negative 141 kilojoule, and then the oxygens must change to all 2 negatives, so the value is positive 750 kilojoule. And then we know that this is the enthalpy of formation is negative 414, and the lactic acid is given by the tables is also negative 2478 kilojoule. The second question is calculate the enthalpy of atomization of sodium. To reverse the Hess law, say that the change of enthalpy is the same no matter the reaction take one state or several states. So we just sum out the change of enthalpy equal to negative 414, and our target is find the enthalpy of sublimation. So negative 414 equal to 2A plus 992 plus 249 minus 141 plus 750 minus 2478. We just calculate it, and we can get the answer is positive 107 kilojoule per mole.
So moving on to the next question, by using the following data, construct the Born-Haber cycle for NaCl in solid state and calculate its lattice energy. So now the question is giving us the enthalpy of atomization for sodium, enthalpy of atomization of chlorine, and ionization energy for sodium, electron affinity for chlorine, and enthalpy of formation of NaCl. So in order to construct the Born-Haber cycle for NaCl, first thing first, we have to write down the chemical equation for the formation of NaCl, which is this one. We write it down here. Na react with Cl2 produce NaCl. And after writing down this equation, don't forget to write down the enthalpy of formation of NaCl and here, which is negative 411 kilojoule. This is the first step. The second step is we have to convert the Na into sodium gaseous atom and Cl2 into chlorine gaseous atom. This second step involves the enthalpy of atomization. So we can see here enthalpy of atomization for Na is positive 109 kilojoule, and enthalpy of atomization for chlorine is positive 1 to 1.5 kilojoule. For the enthalpy of atomization for chlorine, we have to divide the value given in the equation by 2, because the question gives us 1 mole of chlorine, but our equation is 1/2 mole of chlorine. So that is the second step. The third step is we have to convert the sodium gaseous atom into sodium gaseous ion, and we have to convert the chlorine gaseous atom into chloride ion in gaseous state. So if we want to convert the Na into Na+, we have to use ionization energy, because ionization energy is the minimum energy required to remove 1 mole of electron from 1 mole of gaseous atom or ion. So here the ionization energy is positive 496 kilojoule. And if we want to convert the Cl into Cl-, we have to use electron affinity. Electron affinity is the energy change when 1 mole of gaseous atom gains 1 mole of electron. So we use electron affinity, which is negative 349 kilojoule. So the last step is we write the chemical equation. Na+ react with Cl- produce NaCl, and this is our lattice energy. The question asks us to calculate the lattice energy, so we have to know that H overall is equal to H1 plus H2 plus H3 plus H4 and plus H5. So we can substitute all these values in that equation and find the lattice energy. So the lattice energy of NaCl in solid state is negative 788.5 kilojoule per mole. If the question asks us to construct the bond-Haber cycle of NaCl in energy level diagram, we can start from here. First, we have to write down the chemical equation for the formation of NaCl. The arrow is pointing downward because the enthalpy is negative. So if the enthalpy is positive, the arrow will be pointing upwards. Then next, the second step is we have to convert Na into sodium gaseous atom and Cl2 into chlorine gaseous atom. So we have to use the enthalpy of atomization, which is H1 and H2 here. Then the third step is we have to convert the Na into Na+ and Cl into Cl-. Then we have to use the ionization energy, which its enthalpy is positive, and electron affinity, which its enthalpy is negative. Then finally we can find the lattice energy. That's all for this question.